Okay, so thanks for the introduction. Go ahead to the next slide. Thank you. So I'd like to speak on some topics here related to the lunar reference frame and asked to address these specific issues of why does the lunar reference frame matter, the common assumption that all data is in the one frame, when of course it's not. What issues are there about these frames, if any, and what impacts might there be on your work, on everyone's work? Mostly be addressing, as Sam mentioned, the Lunar Exploration Analysis Group white paper that I and my co-authors did on this. It was released last September, and it's available on the main league website under the news item. So next slide, please. So as some background on this, I should point out at the start that I'll be using the terms coordinate system and coordinate frame, and they actually have slightly different meanings. That a system is an overall concept, while the frame is a specific realization of a coordinate system. In other words, an actual set of coordinates of points on a body surface. So for the moon, there are two reference systems, the mean Earth polar axis, or ME, system, and the principal axis, or PA system. The mean Earth system is defined from the moon, or the Earth defining 0 degrees longitude from the direction of the moon, and the mean direction of the moon's polar axis defines latitude on the moon. And this has been in use in some form since the 18th century for essentially all mapping of the moon. The principal axis system is defined by the three maximum moments of inertia of the moon, and this is important for dynamical and gravity field studies, particularly for spacecraft force modeling near the moon, cislunar space. So the difference between these systems varies depending on where you are, but a maximum is 875 meters. And this is due to the asymmetry in the moon's gravity field. It was discovered during the lunar orbiter missions in the 1960s. So this is obviously important for most purposes where we have, for example, meter level data. So the next slide, go to that, covers more background, and this time about the frames. The actual frames are derived from observations of the lunar laser ranging retroreflectors on the moon and solutions done at JPL and the IMCCE in Paris. These solutions are done in a principal axis system, so they always make principal axis frames by providing positions for the retroreflectors. Successive solutions will change some internally and a little bit in orientation, right now probably at the meter level or less, but they still change due to having different data sets, changes in modeling and parameters, and they'll eventually change due to having different data sets being added to these solutions. And so there are shifts in orientation, minor but real, and so this is not an ideal system for doing accurate reference frame for mapping. The ME frames are based on the principal axis solutions, so they're internally identical to those solutions. However, the orientation is based on, for example, DE 421, the mean direction of the Earth. And now updates to that are no longer based on actually determining where the Earth is, but making a comparison to the DE 421 frame and doing a no-net rotation from that frame. So the idea is that these frames are now going to be locked to the lunar surface, assuming that surface feature coordinate changes are minimized. That's the goal. So next slide, please. So why does this all matter? Of course, I've already mentioned the uses, PA for gravity fields, topography, ME frames for mapping. And for most users, all this is transparent because in the background, the lunar ephemeris is generated along with these frames, and it's the ephemeris that's used to determine the orientation of the moon, and then lunar data products, for example, from LRO or other missions, and all data and products are based on that system and that ephemeris. So in the end, surface coordinates for mapping are based on ME systems and frames, and this has been recommended by many groups throughout the entire space age, from the IAU Working Group on Cartographic Coordinates and Rotational Elements, the LRO mission and the International Lunar Geodesy and Cartography Working Group, the NASA Planetary Data System, the Artemis 3 Science Definition Team, the Lunar Critical Data Product Special Action Team, the current Artemis Geospatial Data Team, the League and the NASA Planetary Science Advisory Committee. So essentially all known missions internationally are using the NME system and frames for mapping and navigation. So there's a story here of an international standard success where everybody is using the same thing for mapping. So on the next slide, so what are the issues here with these frames? It's been proposed that a principal axis system-based frame be used for all use, including surface mapping and navigation. And concerns have been expressed about the higher accuracy is needed in the long term, that there's the current use of both frames, which may be confusing, and also maybe a better connection via the principal axis frame to the lunar structure, geophysics, via the lunar laser ranging and gravity field solutions. But the authors of the white paper have looked at all these uses and basically recommended an ME frame should continue to be used for mapping and PA frames can continue to be used for dynamical purposes. And again, both the League and the PAC have endorsed those conclusions. So in the next slide and the following slides, I'll talk about the actual 4 findings that we came up with. The first is about the difference in coordinates being rather large, several hundred meters, and as the first bullet notes, up to 875 meters, and this seems extreme compared to the resolution of current data sets. The image on the right, for example, shows an LROC image of the Apollo 14 landing site. The star at lower right represents where the landing occurred, and the colored lines represent the EVA paths. If you accidentally would use the wrong coordinate system, if you use a PA system instead of the ME system that the image is in, you'd get a point up in the far left corner, 842 meters away. And if you use this somehow for surface or rendezvous operations, of course, you could have serious problems. So in general, this is why when any, not just the moon, but lunar and planetary coordinate frames are updated, the idea is to keep the magnitude as small as possible and close to the resolution of the data. The next slide goes into the second finding, which is about the accuracy of these frames. And again, the primary difference between these frames is in the orientation. Aside from the offset between them, when actual updates are made, the updates on the ME frame are made with respect to the previous frame so that surface features maintain the same coordinates at the accuracy of the solution. So at the sub-meter level, the principal axis frames are not quite the same and will drift in relation to the surface, whereas the ME frames will not, at least at the level of accuracy of the solution. And this procedure is similar to what's used for the Earth in creating the International Terrestrial Reference Frame updates, where a no-net rotation solution is made. So the next slide mentions the third and fourth findings, which are basically about the data volume and confusion between the data sets. As the first bullet notes, any plan to use the PA system for mapping and navigation would involve some conversion or use of new data sets in a different system. So this requires new knowledge and new funding to do this work. It is feasible, it is possible, but it's extra work and funding and time. And it would be a massive undertaking if a decision was made to convert existing data sets. But even if you start to do this piecemeal and convert data as needed, you create an interoperability problem of having data sets in different frames. So users would have a big issue because they now have to start carefully checking for which frame is used. Some users may never switch to using an ME, away from using an ME frame for mapping, and this could result in confusion lasting indefinitely. One final point is that it has been proposed that the current use of 2 different frames for lunar missions may be confusing, but these missions use many frames. To our knowledge, this hasn't been an issue that's been reported. And also, if there's a desire to use one frame, a single gravity field could be rotated into an ME frame and that used, as opposed to rotating lunar mapping into a PA frame, so that could be used. So we'll go on to the final slide here, just to have some final comments. The most important point here is the first one, that just in general, and this is why I'm presenting, the community needs to be aware of these 2 systems and frames and their possible uses. If a PA system-based frame begins to be used for mapping and navigation, users will have to take much more care about which system the data and products that they use are in. The NASA Federated Board has created a working group to make recommendations regarding the use of lunar reference frames, and Robin Ferguson will be talking about that next. But no matter no matter the outcome, I think it's obvious that better international cooperation on lunar standards would be useful, either as an expansion to existing work to create the lunar spatial data infrastructure, which we'll be hearing about in a moment from Jay Laura, or perhaps as an international lunar year project related to the presentation that Erica just gave. So thanks for your attention.